argument, right, is the fact that I just determined the order of a graph containing the factorizations of identity, but not the ones containing only the transitive ones, the ones whose entries generate the entire symmetric group. But I only care about the transitive ones. It turns out that I prove that, in fact, the number of transitive factorizations is very, very, very close to the number of factorizations in general. Why? Well, the probabilistic argument is like this. If it's not transitive, and you have a very large factorization, right? The chances, I'm sort of paraphrasing the proof, the chances that one transposition will not show up in that very long, increasing length L tuple is 1 out of, all of them. 1 out of a really huge number. And as L increases, what do you have? You have that it tends to 0. And so in general, this is the reason that the transitive factorizations for long enough L end up being pretty much close to the number of total factorizations of identity. So again, I went to probability. There is a place for it in this sort of geometric question. So moving on to the big theorem, the diameter of the Hurwitz graph. Oh, I have time. This is the technical stuff, but it's very nice, in my opinion. Humble. Okay, so this is what I do. So, we want to know how fast the diameter of this graph grows with respect to the order of the graph. I mean, this is really the question. Because the order of the graph being a fraction of the total number of these factorizations, the total number of factorizations is what? It grows exponentially. It's n squared, what is it, to the L, right? So you take all the transpositions to the L power divided by the order of the alternating group, and this is somewhat the size of this graph, up to a constant, right? This is huge. As L increases, this might mean that it might be very difficult to get 2 Hurwitz equivalent L tuples and to find some sort of a path between them. The diameter may grow very, very, very quickly. But we want to know about this. So, initially, it seemed like a tough question to begin with, because as I said, the Hurwitz moves are the braid action on a finite set of elements of L tuples. I was thinking maybe I'll take some quotients of the braid group. In other words, I'll cut down the braid group into simpler pieces and see what happens. The problem is that the braid group is an infinite object. It's an infinite group. And so I'd have to cut it down with other infinite groups. And indeed, this is sort of like really, really, really hard to find a nice quotient of the braid group to begin with. So I abandoned that idea pretty quickly. And I just started thinking about the algebra of the Hurwitz moves themselves, right? And to do so, I was reading this book. I mean, not book, rather, this paper by Itzhak and Teicher. I mentioned it before. And they proved many, many nice things about Hurwitz equivalence in the symmetric group. And using some of their techniques, I was able to develop some of my own techniques, and then finally get a solution for this.
Can you please write the names on the board?
Sure. So it's Ben Itzhak and Teicher.
Mina Teicher.
Yeah, Mina. So, lady. Anyhow. Where was I?
You read the book.
So this is, they establish, or they come up with, this sort of what we call a canonical factorization of identity. And it is this that you see up there. And it turns out that they show that these Hurwitz graphs that we have are all connected. And they're all connected because they all connect to this one. And they showed not an explicit way of getting there, but they show that it's possible to transform all of them to this. So if they're all connected to the same vertex, then they're all connected, clearly. So the idea actually stems from this sort of canonical factorization. And so instead of using their argument, which was very cumbersome, in a sense, it took too many moves. It was very, very difficult, and it was done by induction. And so it's not very clear how efficient this was. I started from here and started to think, okay, what can we do? So what I ended up thinking was this. So let's say we have a factorization. Let's call them alphas, just to change it up. L minus 1, alpha L. And assume that this L is much larger than N, which is what we were dealing with in this project. The first thing I decide is, well, I don't like the form. This could be anything. All of these transpositions may have no order. They are chaotic. So I said, okay, let's give it some order. So how to give it order? I thought, well, let's take pairs that are the same, put them next to each other, right? That makes it a little bit easier to deal with. So what I do is, by the pigeonhole principle, Dirichlet principle, as I've heard, we can take and choose 2 plus 1 of these and find 2 that are the same, at least. And so what I end up doing is, I end up sort of pairing them off in even numbers. Right? So then every pair, I go down the entire word. This is a word of transpositions. And each of these is a letter. I go through the entire word and I start pairing everything off, pairing them off. And at the end I have a tail. But the tail is generally easy to pair off again. So this is not a big deal. And they wanted me to figure out how long this would take. And it turns out that each time it's only some multiple, some multiple of n squared for each of these moves, times L, let's say. Because I have to go down the entire length of this word, right? So there's L many, but they only travel in this window that I keep moving, see? And then I have this, and so, the reason I can move them is because of the fact that I can do inverse moves. I can move them this way and keep them invariant. Of course, it will change some of them as I sort of leap over them. So, for example, if I have A1 and I have, A5 and A6 is actually equal to this one, I can sort of jump, move by move. It will change these guys in the middle, but that's not that important. And so, I get this. But this is not a big deal. This is not a lot. These are not a lot of moves. So I turn everything into something called pairs form, which is one step closer to the canonical factorization by the fact that all these things are sort of paired off. What's the next thing I do? The next thing I do is I take pairs that act transitively on the group. I just find them in the entire word. So let's say I now have beta 1 and so on. Beta L. And these guys are in a paired off form. So I take some of them that are transitive and I move them all the way to the front of the word. So let's say I send them over here. So let's have 1, and so on. And I'm going to have actually how many of them? N minus 1? N minus 1 of these pairs. 2 times n minus 1 of these guys. And so on. So far, so good. And here's where the ingenuity comes in. what I end up doing is I know that within n squared moves, I can turn this into this form. 1, 2, 1, 2, and so on, n minus 1, n minus 1, n, and the rest are all different, these gammas. Without affecting the gammas, I can change all of these into this canonical factorization. And here's the nice thing. Since these are in pairs form, there is a certain combination of Hurwitz moves that takes each pair and converts it. It converts it into a 1, 2. See? And I move every element here down the word. So I end up, in a sense, eating each pair with this little machine that I've created. And it takes a pair, converts it to 1, 2, drops it off. So let's say I took these two. This is my original. I'm going to underline it because it's the original one. And then I have the next two. And I do it again. This was, I got 2 of them, so I'm at 3, and so on. Why is this useful? Because now it means that I only need to move the rest of them only this distance every time. Only the distance 2n minus 1. Which means that I can do this in, again, a linear number of moves, n times L. And I'm done. And that's it. And so I run this throughout the entire word and I get exactly the canonical factorization. But I do it in a linear number of moves with respect to L. So it means that actually the diameter of this thing, though it's an exponentially growing graph, the diameter is kind of linear only with respect to the length of the L tuples that I'm dealing with. See? This is very nice to know. It means that it's not so hard to have these, to show that 2 of these factorizations are equivalent. Not at all. And in fact, this graph is actually pretty tightly well connected. And in general, that was the whole thing that I did. And it was rather surprising because we expected that because a geometric problem is so sort of like more difficult and there's so many ways to turn one covering into another, that he expected it to be much more difficult, not linear with respect to the number of these branch points. And that's it.
That's it? Nice.
Any questions?
Questions?
Can you explain again how is it that the underlined part? So when you apply that to the pair, what is it that is happening?
What I do is I wave my hands. Okay, we'll do one pair for you. Pick a transposition, your favorite. 1, 3. Okay, 1, 3. This is what I can do. Since these are disjoint, agreed? I can do a Hurwitz move, and when you conjugate it, they commute. So the conjugation does nothing. It leaves it fixed. For example, if I jump this way, if I do this Hurwitz move, then I'll get 1, 3 conjugated by the inverse of this. I mean this and the inverse of this, and then this one moves to this position. But these are disjoint, let's say, right? For n large enough. So that means that these guys commute. So these cancel. Agreed? And so what I do is I leap over 1, 3, both of them actually, until I get all the way back.